So the last piece is using Newton's second law to put all this stuff together. And the thing about Newton's second law is, and okay, I'm not trying to be like obvious here, but there's two sides to this equation. One side is the sum of forces. That's what happens when you add up all the forces. The other side is mass, which is the amount of stuff in an object, times acceleration, which is this change in velocity. Here's how it works. We can do this 3 times. We have 2 dimensions for our cart and 1 dimension for our hanging mass. For our cart, let's start in the x dimension. So the sum of the forces on the cart in the x dimension should equal its mass times its acceleration in the x dimension. This is where a lot of times people are like, okay, well, sum of forces is equal to, you've got a number for this, 1.3 kilograms, you've got a number for this, 0.8. You multiply them together, you're going to get 1.04, and you're like, okay, now what? But you have another side of this equation. This means mathematically add up all the forces. Here's how you do it. We have one force in our negative direction. All forces are always positive in physics. If we have a force in a negative direction, we put a negative sign in front of the force or the variable. So the force of friction in our negative direction plus our tension force in our positive direction will equal our mass times our acceleration. What we know for this cart is the force of friction, it's 0.02. We know the mass, it's 1.3. We know the acceleration, we're targeting 0.8. So that means ultimately the more useful algebraic form of this equation is going to be that the tension is going to be equal to the mass of the cart times its acceleration plus the force of friction. Okay? And when you do this, you should find that this is 1.04, this is 0.02. So that means our tension needs to be equal to 1.06 newtons. Now, if you used a different mass, if you used a more precise mass, like the carts don't weigh 1.3 newtons with 2 bars. It's a little bit less than that. So maybe you used 1.285 newtons. And if that's the case, then kilograms. So if that's the case, then your tension is going to be a little bit less too, but not much. We also have a y dimension in our cart. In the y dimension, the sum of the forces is equal to mass times times acceleration in the y dimension. It's not accelerating in the y dimension. We know that, not because things never accelerate in the y dimension, but because in this particular problem I told you, it's going to move left and right only. There will be no up and down motion. That means no up and down acceleration. That means the sum of the forces in our y dimension have to be 0. We have two forces. The normal force is in our positive direction. The weight of the cart is in our negative direction, so I'm going to put a negative sign in front of it. That's going to equal 0. I'm going to stop there because while we could find the normal force, we don't need to. So it's not that this isn't correct, it's just that's not going to end up being useful. Okay? When we look at the hanging mass, it only has one dimension with anything going on. In the x dimension, there are no forces, so the sum of the forces is 0. And there's no motion at all, so the acceleration is 0. So mass times acceleration is 0. Left and right, for mass 2, 0 equals 0. Not super helpful. But in the y dimension, for the hanging mass, the sum of its forces should equal its mass times its acceleration. What are the forces acting on this mass? Well, there's an upward force from tension. That's in our positive y direction. There's a downward force force of gravity pulling it straight down. That's in our negative direction. That should equal mass times acceleration. So again, this is like accurate for this particular scenario, but it's not the most useful thing in the world in terms of the algebra, because while we do know the tension, it's what we just found here, 1.06. We know g, it's about 10. What about acceleration? And we're trying to find mass. So let's solve this equation for mass. If we add m2g to both sides and switch sides, algebraically we get this. m2 times the acceleration plus m2g will equal tension. The algebra here involves factoring m2 out from both sides. m2 times the acceleration of the object plus g will equal our tension. If we divide both sides by this quantity, we can find the mass is going to be tension divided by the acceleration of the hanging mass plus g. We know the tension, it's 1.6. We know g, it's 10. What about the acceleration? Well, this is where there's a little bit of logic and a little bit of math here. The logic involves recognizing that for this particular setup, we absolutely have to have the same acceleration for both of these objects. I talked about that already. The string isn't bunching up or stretching. They're maintaining their positions relative to each other. So if the cart is accelerating at 0.8 meters per second squared to the right, the mass is accelerating at 0.8 meters per second squared down. Here's the problem. Down for the mass is its negative direction. With forces, the sign of a force is always positive. That's going to be our convention in this class. If we have a force that's in the negative direction, we'll put a negative sign in front of the variable. For acceleration, that's not how it works. In this case, the acceleration of our mass, AY, is equal to negative 0.8 meters per second squared. For forces, if we have a variable, it's always going to equal a positive number. That will make the left-hand side of Newton's law work better for us. For acceleration, or velocity, or displacement, the variable might equal a negative number. That's going to work out better for finding unknowns, because much of the time we won't know what the acceleration, what the direction of acceleration is going to be. We're trying to find it. So what we want is to be able to say, oh, if my acceleration is positive, it's accelerating in the positive direction. If my acceleration is negative, it's accelerating in the negative direction, right? So in this case, our numbers are going to be 1.06 divided by negative 0.8 plus 10, and that ends up being 1.06 divided by 0.92, and that ends up being about 0.115 kilograms. So that is all of our theoretical stuff. Okay? Our theoretical stuff is how much pulling force do we need? We just figured out it needs to be 1.06 newtons. How much mass do we need hanging off the pulley to get there? About 0.115 kilograms. About 0.12 kilograms. That's 120 grams. So here's the key. Just recognize, all of you, and anybody who's listening, just recognize, I don't expect you to be able to do this yet. I expect that you are going to see this as a target. This is where we're going. The only way to get there is by, we're just going to launch. And so that's what we're doing. The homework problem is similar but more complicated. The example I gave in class, similar but actually more complicated. So go back and watch that video. This video will be available for you. I'll go over the homework on Tuesday. We're just going to keep hitting this stuff over and over until you get the practice and until you achieve the skill level that you need. So if you're not getting it now, don't panic. You will get it. It takes time and practice. That's what we're gonna do.